Section 1.3, Angular and Linear Velocity. On this slide, we're going to be converting units. Follow along. It says perform each conversion. Round answers to the nearest tenth. So what we're going to have to change from problem number 1, we're going to have to change 60 revolutions per second to X amount of radians per second. We're going to be using the following fact that 1 revolution is equal to 2 pi radians. You saw this in section 1.2. So now I'm going to express this as a ratio, 60 revolutions over 1 second. And my goal is to change revolutions to radians. So I am going to multiply this by 1, or the following ratio, which is going to come from here. And I'm going to express it the following way. 2 pi radians over 1 revolution. Now at this point, you should be able to see why I expressed this the following way, because the revolutions, these units, are going to be able to disappear, and all I'm going to be left with is just radians per second. So once I multiply, this is what I get, and at this point all I need to do is round to the nearest tenth. So I take 120 multiplied times pi, that is built into the calculator, and this is what I get. 377 radians per second. Let's go to number 2. Now in this problem, I'm going to be changing 3000 radians per hour to X amount of revolutions per second. Very similar to number 1. It's going to take a little more work. But again, I'm going to express this as a ratio. 3000 radians over 1 hour. So I am going to get rid of the hours and I'm going to change them to seconds. And I'm going to be using the following ratio. 1 hour is equal to 3600 seconds. This is going to go away and I have radians per second, but I'm not quite there yet. I need to change this to revolutions instead of radians. We'll do that in the next step. I simplify this. This is what I get. Now my goal is to change, like I said, radians to revolutions. So I use the following ratio, which comes from here again. 1 revolution is equal to 2 pi radians, but I express it with 1 revolution in the numerator and radius in the denominator, because this will allow me to get rid of the radians. And my answer is going to have revolutions, and this is what I wanted. So once I multiply this, use my calculator to round to the nearest tenth. This is my answer, 0.1 revolutions per second. Let's go to the next slide. Here's problem number 3. This is angular velocity. This problem is going to be a little more challenging because it's a word problem. But let's just follow this. It says a windmill for generating electricity has a blade that is 30 feet long. Depending on the wind, it rotates at various velocities. In each case, find the angular velocity. So we're going to find the angular velocity. I'll give you the formula in just a little bit. And we want this in radians per second to the nearest tenth for the tip of the blade. So here's the formula. The formula says the angular velocity, and this is a symbol called omega, of a point in motion on a circle through an angle alpha, and alpha has to be in radians, and time t is given by the following. The radians over the number of radians over the time. So angular velocity, let me say it again, is the number of radians over a specific time. So to find the angular velocity of a windmill that is rotating at 11,000 revolutions per hour, all I need to do is I'm going to have to change this to radians per, in this case, second. And that's what you did on the earlier slide. To find the angular velocity, given revolutions per hour, I need to change them to radians per second. So again, here's the formula. Change this to radians per second. So let's get rid of that formula. So I'm going to express this as a ratio, 11,000 revolutions per hour. And then I'm going to multiply this by 1 hour over 3600 seconds. That will get rid of the hours, and since I want seconds. And then also I'm going to multiply this by the following ratio of 2 pi radians over 1 revolution, and that will get rid of the revolutions. So once I get rid of all the units that I do not want, I'm going to be left with just radians and seconds. So once I do that, this is what I get, and this is the answer to problem number 3. We'll continue with the following problems in class.